In this video we will explore the core concepts of exponential functions and models, focusing on their algebraic representations, practical applications and graphical transformations. Let's begin with the standard representation of an exponential function, f of x equals a multiplied by b to the power of x, known as the base multiplier form. In this form a represents the initial value, which corresponds to the output of the function when x equals 0. Graphically, this is the y-intercept at the point 0, a. The variable b represents the growth or decay factor. If b is greater than 1, the function exhibits exponential growth, resulting in an upward sloping curve. If b is between 0 and 1, the function represents exponential decay, characterized by a downward sloping curve. The variable x represents the independent variable, typically representing time or cycles. When relationships are described in terms of a percentage rate of change, we often use the percentage rate form. F of t equals a 1 plus or minus r to the power of t. In this model, a is the initial value at t equals 0. The variable r represents the percentage rate expressed as a decimal. For example, a 4% increase corresponds to an r value of 0.04. The term 1 plus r acts as the growth factor for increasing quantities, while 1 minus r serves as the decay factor for decreasing quantities. The variable t represents the units of time over which this change occurs. A key concept tested on the SAT is distinguishing between linear and exponential behavior. While linear functions have a constant absolute change per unit of time, exponential functions exhibit a constant relative or percentage change. Mathematically, linear growth involves repeated addition or subtraction of a constant value m, represented by the equation y equals mx plus b. In contrast, exponential growth involves repeated multiplication or division by a constant factor b, represented by the equation y equals ab to the power of x. For instance, a quantity that increases by 5 units each year is linear, whereas a quantity that increases by 5% each year is exponential. In some scenarios, a quantity may change by a specific factor over a set interval of time. If a quantity changes by a factor of b every k units of time, we use the model formula. F of t equals a times b to the power of t over k. For example, if a population doubles every 3 hours, the base b is 2, the interval k is 3, and the exponent becomes t over 3, yielding the function f of t equals a times 2 to the power of t over 3. Similarly, if a substance halves every 8 days, the base is 0.5, the interval is 8, and the model becomes f of t equals a times 0.5 to the power of t over 8. Finally, let's look at the transformations of exponential functions in the form y equals a times b to the power of x minus h plus k. The constant k represents a vertical shift. Adjusting k shifts the entire graph including its horizontal asymptote up or down by k units, establishing a new horizontal asymptote at y equals k. The constant h represents a horizontal shift, moving the graph horizontally to the right if h is positive, or to the left if h is negative. Lastly, to find the y-intercept of a transformed function, simply set x equal to 0 and evaluate the expression, which yields the y-intercept at a times b to the power of negative h plus k. On some SAT problems, you may need to rewrite an exponential expression to determine an equivalent rate over a different period, such as a daily, hourly, or yearly rate. By applying the exponent property listed here, we can adjust the base of our function. Let's look at an example. Suppose the population of a species is modeled by the function p of t equals 100 times 2 to the power of t over 5, where t is measured in years. If we want to express this function with an annual growth rate factor, c to the power of t, we need to isolate the variable t in the exponent. By applying our algebraic identity, we can rewrite the expression as p of t equals 100 times 2 to the power of 1/5 to the power of t. Calculating the value of 2 to the power of 1/5 gives approximately 1.1487. From this rewritten equation, we can identify that the annual growth factor is approximately 1.15, which corresponds to an annual growth rate of approximately 15%. Hopefully, this review has helped you better understand how to solve exponential problems on the SAT test. For the rest of this video, we'll let you explore a few additional practice problems on your own. Take your time, apply the strategies you've learned, and check your work as you go.